The topic for today in our Stats for Sustainable Development series is regression. In this video, we will introduce the concept of plotting a regression line through data, explore the principles behind the ordinary least squares or OLS method, and show how to measure the goodness of fit of a regression line. In my last video, we focused on two variables from the Young Lives study of child development in Ethiopia. The dataset contains information on different aspects of household wealth, including housing quality, access to services, and consumer durables owned by the household. This information was combined to generate a wealth index for every child in the data. We labeled this variable X. We also continued to work with our key sustainable development indicator, height for age. Each child has a Z-score which tells us how far away the child is from the median height of a healthy child of their age. We labeled this variable Y. In video 4, we found that X and Y are correlated with each other, but we couldn't say much about Y. Let's now explore this relationship further. We can start by postulating that there is a causal relationship between the two things, and specifically that this causal relationship goes in this direction. Does increasing X, the wealth of the household, have an effect on Y, the health of the child? In theory, this seems like a sensible postulation. The more wealthy a household is, the more resources it has to put towards nutritious food for the children living in that household. In turn, we know that more and better nutrition reduces the likelihood of stunting and helps young children to maintain a healthy growth trajectory. So this causal pathway makes sense in theory, but does it play out empirically? Knowing the answer to this question matters because it informs, or at least should inform, how we do policy. If you are a government or charity working in Ethiopia and you care about sustainable development, then you may want to target the nutritional health of children. But it's very hard to do that directly. No government or charity can produce healthy children or directly make children grow taller, so we have to intervene somewhere else in the causal chain. Intervening at this intermediate stage shows more promise. We could set up feeding programs and provide nutritious meals for children, but one could argue that such a policy is not very sustainable in the long run. It may be more cost-effective to put our resources towards long-term structural change, such as investment in infrastructure, including housing and water supply, or providing cash transfers or loans to help families purchase what they need to be more productive and resilient. We could envisage such policies having multiple impacts across the Sustainable Development Goals. But will this lead to reduced malnourishment in children? This is, of course, an empirical question. So let's bring back our rather stressed-looking jury that we met in video 2. Recall that the job of a jury is essentially to test a null hypothesis that the defendant is not guilty against an alternative hypothesis that they are guilty. Today we want to test the null hypothesis that changing X does not cause Y to change against an alternative hypothesis that changing X does cause Y to change. We will start compiling the evidence in this video, but unfortunately we won't come to a conclusion just yet, so our jury will have to adjourn until the next video at least. Let's start where we left off in our last video by drawing a scatter plot between wealth on the x-axis or horizontal axis and height for age on the y-axis or the vertical axis. Last time we saw that it's possible to draw a line of best fit through the data. Any straight line through two-dimensional space can be defined by two parameters, the intercept and the slope. Let's call the intercept beta 0. This is the point where the line crosses the y-axis, or the value of y when x equals 0. We can call the slope beta 1. This tells us by how much y changes when x increases by 1. Thus, the equation of the line can be expressed as y equals beta 0 plus beta 1 times x. We call this the population regression line as it represents the true relationship on average between x and y across the population. But not every child in the population will sit exactly on the regression line. To find the specific height for age y of any given child I, we have to add another term for our equation, which we call u. This is known as the error term and tells us how far above or below the line we find the data point for child I. That's a theory, but how do we find beta 0 and beta 1 in practice? After all, there are an infinite number of different lines we could draw through the data. How do we know which of these lines is the best estimate for the true population regression line? Many years ago, statisticians came up with a method. Find the line that minimizes the sum of squared errors. We call this the ordinary least squares method, or OLS for short. So what do we mean by minimizing the sum of squared errors? So to explain, let's start with a simplified example where we have just 5 data points. Let's now draw a line roughly through the data like this. Then measure the vertical distance between this line and each of our 5 data points. These are called the errors. U1 and U3 will be positive numbers as they pertain to points above the line, while U2, U4 and U5 are negative numbers as these data points are below the line. Then we find the square of each of these errors to get 5 positive numbers and add them together. Let's now do the same calculation for another line. We can see clearly here that except for U3, these vertical distances are much bigger. So when we square each of these errors and sum them together, we will end up with a higher total than before. Therefore, as we're trying to find the smallest sum of squared errors possible, this line is a better candidate for the regression line than this one. But how do we find the regression line that gives the smallest sum of squared errors? We can't possibly do this calculation for every possible line through the data, as this would literally take forever. Fortunately, calculus enables us to find a neat solution. It turns out that the line that minimizes the sum of squared errors has a slope beta1 equal to the sample covariance between x and y divided by the sample variance x. Please watch the last video to find out what these statistics mean and how to calculate them. In turn, the intercept can be found by multiplying the beta1 that we've just calculated by the sample mean of x and then subtracting this product from the sample mean of y. We calculated all of these statistics for our data set in the last video, so we can use these results to find that beta1 equals 1.81 and beta0 equals minus 1.38. Notice that we put a little hat above beta1 and beta0. This simply denotes that we're referring to the OLS estimators of the true population parameters beta1 and beta0. Remember from my previous videos that all our calculations are based on a sample of children in Ethiopia, so any results we get from our sample are only our best approximation for what's really going on in the population as a whole. We can use these estimated parameters to draw our OLS regression line. Minus 1.38 is the point where the line crosses the y-axis. We can interpret this as the predicted height for age z-score for a child whose family has a wealth index of 0. The estimated slope of the line is 1.81. This means that if x increases from 0 to 1, then y is predicted to increase by 1.81. Therefore, the predicted height for age z-score of a child from a family with a wealth index of 1 is plus 0.43. Such a child is expected to be taller than the median healthy child. Interpret this with caution, however. We find that no child in our sample has a wealth index of more than 0.8, so we are making an inference about a hypothetical child who is outside our data range. Recall from previous videos we've been following closely 2 particular children from our dataset, whom we've called Mohammed and Maryam. Let's see where we find these 2 children relative to our regression line. As we've seen before from our data, Mohammed has a wealth index of 0.41 and a height for age z-score of minus 0.95. This puts him about here in the xy space, a bit below our regression line. So what does it mean for him to be below the regression line? Well, the regression tells us that given Mohammed has a wealth index of 0.41, he's predicted to have a height for age z-score of minus 1.38 plus 1.81 times 0.41, which is minus 0.64. We put a hat on this value of y because this is the OLS prediction of Mohammed's height for age given our sample. But Mohammed's actual height for age is less than this. This means that there are other factors apart from his family's wealth that are also affecting his height. These other factors are all wrapped up in what we call the residual, denoted by u hat. In other words, the OLS estimate of the error term that we've seen before. The residual for a given child is simply the difference between their actual value of y and their predicted value of y, which in Mohammed's case is minus 0.31. What about Maryam? Recall that she has a wealth index of 0.01 and a height for age z-score of minus 2.13. So she is also below the regression line. We can work out Maryam's predicted height for age to be minus 1.36, which means she has a residual of minus 0.77. As it happens, both Mohammed and Maryam are located below the OLS regression line. Of course, as this regression line has been plotted through the middle of the data, there are going to be just as many children located above the line. And indeed, it doesn't take me long to find one. Let's call her Helen. She is an 11-month-old girl living in the Tigray region. She has a height for age z-score of minus 0.63 and a wealth index of 0.17. This puts her here on our graph. She has a higher height for age than what would be predicted based on her wealth, minus 1.07. So she has a positive residual of 0.44. There's one more thing to look at before we finish this video. So we've seen how ordinary least squares gives us the regression line of best fit, but how can we tell how good that best fit is? This can be measured by a statistic called the R-squared, which is calculated as 1 minus the sum of squared residuals over the total sum of squares. Or like this in algebra. To find the sum of squared residuals, we simply square the residual from each child in our sample and add them all up. To find the total sum of squares, we square the difference between each child's actual height for age and the mean height for age y bar and add them all up, similar to how we calculated the variance in the last video. The sum of squared residuals is always less than or equal to the total sum of squares, and both are always positive numbers, which means that the R-squared will always take a value of between 0 and 1. An R-squared close to 0 means the regression is not a good fit, and most of the variation in y is not explained by our x variable. An R-squared of close to 1 means that the regression line is a good fit, and x does a good job of explaining the variation in y. In our case, the sum of squared residuals comes out at 6,616, and the total sum of squares is 6,786. So the R-squared is 0.025, telling us that our regression has a low goodness of fit. This suggests that wealth, as we've measured it, explains only a small part, specifically 2.5%, of the variation in height for age, and there are likely to be many other factors also determining how tall our children are. Why do we call this statistic the R-squared? Because it turns out that we get the same result by squaring the correlation coefficient R, which in the last video we worked out to be 0.16. In summary, the ordinary least squares or OLS method finds the best fitting straight regression line through a scatter plot. The regression line gives a predicted height for age based on the child's wealth index, and for a given child in our sample, the difference between their actual height for age and predicted height for age is called the residual. And if we square all these residuals and add them together, we can use this sum to find the goodness of fit of the regression line. Thank you for watching, and please remember to subscribe to my channel.